Today I am going to discuss about the introduction to quantum gates and the Bloch sphere. So basically I will discuss about the quantum gates and how it is different to the classical gates. So basically quantum gates are represented by the Bloch sphere, and in this is a 3D sphere, and this is the x-axis, this is y-axis, and this is the z-axis, and the north pole represent the zero state, and the south pole represent the one state. Basically this notation called bracket notation, it is a this notation used in quantum mechanics, and in this sphere any point can represent the state of any qubit. So basically, this is we can say this is the ground state and this is the excited state. So fundamental of qubits. So basically, we can know the classical bits can be either one and zero, but quantum bits can be existing in a superposition of zero and one, and it have a quantum entanglement and quantum coherence that enable to create quantum computation. And basically the qubit can be controlled by gates, which in physical terms it is a microwave. So this is the single qubit quantum gates. In classical, we know that there are multiple gates like not gate, or gate, but in quantum gate, it's bit different. First one is X. So this is the circuit representation of the X gate, and it rotates the qubit state by 180 degree about the x-axis. So this is the representation of x-axis. It is a 2 by 2 matrix, and if we applied the x gate on the zero state, we will get 1, and the vice versa. This is the x gate. The y gate is it rotates the qubit state by pi radians, which is 180 degree about the y-axis, and this is the represent circuit representation, and this is the matrix, and this is the input output with a imaginary part. And in the z-axis, this rotates the qubit state by 180 degree about the z-axis. This is the notation of the z gate, and this is the matrix representation of the z gate. And the input output, if we put if we applied the z gate on the one state, we will get one state but with a negative sign. This is the another couple of single qubit quantum gates. First one is s gate. So basically it rotates the qubit state by 90 degree about the z axis. This is the circuit representation, and this is the matrix. So we see that if we applied the S gate on one state, we will get one state with a phase, which is e to the power I pi by 2. So T gate, so it's rotate the qubit state by 45 degree about the z axis. This is the circuit representation, and this is the matrix. So here we see that if we applied the T gate on one state, we will get a phase which is e to the power I pi by 4. So this is the H gate. This rotates the qubit state by 180 degree about an axis diagonal in the xz plane. This is also equivalent to the X gate followed by a pi by 2 rotation about the y-axis. This is the representation, circuit representation. This is the matrix, and Basically this is the superposition state, which is the probability of getting zero state is 1 by root 2 the whole square, and the probability of getting one state is 1 by root 2 the whole square, which is 50-50. So this is the multi-qubit quantum gates. Basically, the multi-qubit quantum gates, they are the qubit use one qubit to control the operation performed on the another qubit. Basically, it's record minimum 2 qubit. So basically, there is a target one, and there is a target qubit, and there is a which is and the one is control gate. So this is the CNOT, CZ, and I solve gate. This is the circuit representation, and this is the matrix representation, and this is the truth table. So the quantum gates is applied for state preparation, gate application, and measurement purposes. So thank you.